College Algebra. This is section 3.4. We're going to be looking at graphing polynomials. We're looking at something called end behavior and other sorts of things, turning points. And this is going to help us in graphing these certain polynomials that we are given. So let's go ahead and get started. So in graphs of general polynomial functions, the function that we are looking at right now is this right here. And to determine the width of the graph, how we determine that is this value of a. Just like in our other graphs, of not polynomial functions, but any other type of function. This value of a, whenever it is greater than 1, the graph is stretched vertically, making the graph look narrower. And when the value of a is between 0 and 1, the graph is shrunk or compressed vertically, making it look wider. So just like we graphed functions in the last chapter, many of those rules apply here too. And here are some of those rules that we have looked at before that are still going to apply in graphs of general polynomials. So comparing the graphs that are right here to this one up here, we should know that if we multiply our value of a by a -1, looking at this first one right here, it is reflected across the x-axis. Now, the graph of this right here, when we add a value of k to it, depending on whether it's negative or positive, it shifts up or down. And the graph of this one down here, when we add or subtract a value of h to x, the graph is translated right or left, so many units. And then the graph of this right here, it just shows the combination of all the translations I've stated before. So let's graph this function right here and then determine the intervals of the domain which the function is increasing or decreasing. Okay, so what this graph is the x cubed graph, just shifted up 1 unit. So we should know how to do that one already. This is just kind of a review of what we've done before. So let's graph that up 1 unit. And the x cubed graph kind of looks like this. Okay. And the domain for which the function is increasing or decreasing, well, it's actually increasing over its whole domain. So you can say increasing on -infinity to infinity. And we're done. Let's do another example. So this right here is a function that acts like x to the 5th. And x to the 5th looks a lot like your cubing function. Just the cubing function looks like this. The x to the 5th function, right at this point right here, it just gets a little wider is all. So let's graph that. And this x to the 5th function is shifted over to the right 2 units. So over here, okay, looks something like that. Okay, and then now the domain over which the function is increasing or decreasing. Again, this function, over the whole domain, it is increasing. So there we go. On this page here, what is stated are things about the domain and ranges of polynomial functions. So unless otherwise restricted, the domain of a polynomial function is the set of all real numbers. And then this right here means the same thing. It's on that interval, negative infinity to infinity. The range of a polynomial function of odd degree, something that we're looking at a little bit further into this section, is odd degree and even degree functions. But the range of odd degree functions of a polynomial is also the set of all real numbers. So if you have odd degree polynomial, the range and the domain are going to be the set of all real numbers. It's a little bit different with even degree functions, and we'll take a look at those here in a little bit. But also about odd degree polynomials, you'll see that in the next couple of slides whenever I show you some examples of odd degrees. This statement down here, there's going to be at least 1 0 for odd degree functions. Can't say that about even degree functions. There might be imaginary zeros, or only imaginary zeros for some even degree functions. But odd degree functions are always going to have at least 1 real zero. So here are some examples of odd degree functions, and the reason they always have at least 1 real zero is because of their end behavior, which we're going to be looking further into also, is something called end behavior. Odd degree functions either begin in negative infinity and go to positive infinity, meaning that it's going to have to go through the x-axis at one point. And over here, this one right here, this graph, see, this function is an odd degree function, but it starts, again, negative infinity, goes to positive infinity. Just, it's flipped the other way around along the x-axis there. So, here are 3 odd degree functions, and you can see that all of them have at least 1 real zero. That's what we're showing here. The behavior of graphs at zeros depends on the multiplicity of the zero. So we're going to be looking at multiplicities again, which we've studied a little bit in the last section. But multiplicity is this right here, when we have a factor that is being taken to a power, like 2 or 3 or 4. But when we have a single multiplicity, when we do not have a power on our function or on our factor, does not have a 2 here, there's a 1. This is how it goes through the x-axis. It simply just goes through the x-axis, okay? Either this direction or this direction, okay? Now, whenever a graph or your function has a multiplicity that is an even power, so say we have the factor x minus 1 again, and we're squaring it, or it's to the power of 4, 6, or 8, you know, any even power, what the graph at that x value, or the 0, what it's going to look like is this one of these right here. It's just going to turn or bounce off the x-axis, but it's going to touch it there at that factor, okay? So it's going to either look like this or like this. So this is giving you some ideas of how to graph some of these functions that are in factored form and may have multiplicities. Now, if your graph crosses the x-axis at a 0 that has a multiplicity that is odd and is greater than 1, the graph just kind of wiggles across the x-axis like this right here. So, anytime we have, need my pen, something like this right here, this is what we're going to have. This is what the graph at that x value is going to look like that or like this. Now, something about polynomial functions of even degree. It has a range of the form this right here or this. Never both of them, just one or the other. And if you look at both of these graphs that I have down here, you can see this is the value of k that this thing is referring to up here, these intervals. Our functions that are even degree either begin at a k value and go to positive infinity, or we begin at negative infinity and go up to that highest point of k. So that there is why the even degree polynomials are different. And all of these graphs show that we have zeros on our x-axis there. But it's a possibility that our polynomial may not even, or an even degree polynomial may not even touch the x-axis. Like it can look like something like that. And never even touch the x-axis. And that is still an even degree polynomial. It doesn't have real zeros, it has imaginary zeros. So we're going to be looking at something called turning points in behavior. Turning points are this right here. Whenever we have functions of odd degree or even degree, they have things called turning points, and that is when the graph changes from being increasing to decreasing or decreasing to increasing. So a point or points like this. So here's a turning point right here. At that point right there, it changes from being decreasing to increasing. Same goes with this one right here. Changes from increasing to decreasing, and then again. See, all three of those are called turning points. Now, for turning points, to determine the number of turning points your graph has, it is going to be at most the degree of the function minus 1. So say I have the function f of x equals x cubed minus 2x plus 1. Say I have this function right here, and I'm trying to determine the amount of turning points. Well, there's going to be at most the degree of the function 3 minus 1 turning points. So there's going to be at most 2 turning points for this graph right here. Something called in behavior of polynomial graphs are always determined by the dominating term. And we're going to be looking at this in the next consecutive pages that I have in this presentation for you. Okay, so the dominating term in your polynomial is always the one that has the highest degree. It's where you determine the degree of the function. So this function right here is going to have the same in behavior as the piece of it that I just circled. Okay, so let's look at that further. Now the in behavior of a polynomial that looks like this down here, this function. Our dominating term is this 2x to the third. So our graph is going to look exactly like what you see, but the in behavior is always this. It is going to begin somewhere in the negative infinity range and then go up to the positive infinity. So that's where it begins and ends. That's why this is called in behavior. You know where it begins and you know where it's going to end. So this is how we state our in behavior sometimes, is as x goes to infinity, so as our x values go this direction, our y values go to the positive direction. And then same over on this side, the negative x value side, as it goes to negative infinity, our y values go to negative infinity. Now looking at the in behavior of this graph, it is odd degree, but our leading coefficient here is negative. So it's going to be kind of the opposite of what we were looking at before. As our x values increase or go to positive infinity, the graph falls. It goes to negative infinity. As our x values on this other side decrease, goes to negative infinity, our y values get bigger. They increase and go to positive infinity. So here's a little bit about odd degree polynomials, a portion of it anyway. So suppose that our dominating term is this right here, ax to the n, and what's going to determine our end behavior is this leading coefficient right here, and whether it's positive or negative. And in this case, we're stating that it is positive. So if our degree of the function is odd and our leading coefficient is positive, this is the shape of the graph right here. It is going to start in the negative infinity area down here and go to the positive. But the reason it has this dashed line, we can have any sort of curvature shape that goes inside here. So we can have something that looks like that. Okay? This is similar to the last one. It's an odd degree, but our leading coefficient is being said that it is negative. So our graph here, the way it looks, kind of flips across the y-axis. And so we begin in the positive infinity range for our y values and end in the negatives. And then again, what's in the middle here can be anything. Okay? Okay, so here are some things about end behavior polynomials, but our degree of our function is even. So whenever our leading coefficient here is positive and our degree is even, this is our end behavior, how we state it, but this is how it looks right here in this graph. In our negative x area, we start in the positive y values, and then in our positive x area, we end with the positive y values. So it has this shape that you see right here, but like you saw in the last one, this little dotted area, we can have any sort of shape at this point, as long as it's a smooth curve. So it can look something like that. Now our end behavior here, we're looking at, again, even degree polynomials, but our leading coefficient is negative. We have a shape of our graph that looks like this. The negative x values, the y values are negative, and then it goes up, and then it ends in the negative y values on the positive x side. And it looks like anything in the middle here. Okay, here's an example about what we've previously discussed about end behavior. We're going to match all four of these functions to these four graphs here. There's one for each of them. And I kind of expect y'all to do this too. And we are not going to be using a graphing tool at all on this. We're just going to be using what we know about end behavior to determine which of these four graphs belong to each of these four functions. Okay, so looking at this first one, f of x, the leading term here is x to the fourth, so it's an even degree polynomial, and it's also the leading coefficient is positive. So if it's positive and even degree, remember the shape of the graph is going to begin in the positive y area and end in the positive y area. So it's this one right here, it's C. let's look at g of x. Its leading term is also even, but it is negative. The leading coefficient is negative. So it is going to look a lot like c, just flipped across the x-axis. So that right there is a. Now let's look at h of x and k of x. Here we have a leading term that is odd degree, and the leading coefficient is positive. Let's also look at this one. It's odd degree, and the leading coefficient is negative. So when it's odd degree and it's positive, remember our end behavior looks something like this. It begins here, ends here. So that is b for our function of h. And then last that we have, the next one is d. But like I've stated before, our end behavior looks like this. Begins here and ends there. So that's how you're going to determine or match graphs to different function is by end behavior. Here are some steps of how we're going to sketch graphs of polynomials. Step 1, we're going to find all the real zeros of the function, and then we're going to plot them on our x-axis. And step 2, we're also going to find the y-intercept, and then plot that on our y-axis. And then step 3, we're going to use end behavior to determine where it begins and where it ends. And then we're also going to be looking at multiplicities and things to determine if we either cross the x-axis in a way, or bounce off of it, or wiggle through the x-axis. So that is how we're going to do the next example when we're going to graph this next function. Okay, the thing about this function here, it's already factored out for us. Sometimes there's maybe a couple of homework problems. I'm going to make you factor it first, and then from there graph it. And you're just going to be factoring it like you've done in the previous section to determine zeros, use your synthetic division and things like that. But here it's already factored, so to determine the x-intercepts, not so bad, just set each of these factors equal to 0 and solve. So x-intercepts are at x equals -2 and 1. So right here we're going to plot an x-intercept, and right here. Now we're going to determine, that was step 1, sorry guys. Step 2, we are going to determine the y-intercept. And remember, y-intercept, you replace all your x values with 0 and solve for your y. So do this. Oops. Place that x with 0. Square it. So our y-intercept here is 8. So plot that on your y-axis. That's terrible. There we go. There's our y-intercept and our two x-intercepts. Now the last one, we are determining end behavior and how the graph crosses the x-axis at these x-intercepts. So to determine end behavior of something that is already in factored form, this is how you're going to do it. You're going to look at the powers, and you're going to add them together. So this function right here is going to act like an x to the 5th, and neither x value here is negative, and there's no negative on the outside of our function, so it is going to be just like this. The end behavior is going to act like a positive x to the 5th. So it is going to begin down here and end up here. Now, how it crosses the x-axis is determined by the multiplicity of each of these factors. So where it crosses the x-axis at -2 is determined by this multiplicity right here, 3. So if it's odd degree, remember, and it's greater than 1, it's going to wiggle across the graph. So since it begins down here, it's going to wiggle across the graph like that. And then for this one, the x-1 factor, it's going to bounce off the graph. And because it ends up here, it's going to bounce off the graph like this. Okay, now let's determine how the rest of the graph looks. So there, we got to connect it to the y-axis up here. And come back down. And then go back up. There you go. There's a sketch of what our graph of f of x here is going to look like. In this next slide, I have what it looks like exactly, so let's see if we got close. Alright, so we got pretty close to what the graph actually looks like. Another thing to note about graphs of polynomial functions is I may give you a graph that looks like this, and you have to determine the function. And we're going to do that a lot like what we've done before with graphs of functions. We are going to locate the x-intercepts. So here's an x-intercept, here's an x-intercept. But this time we're going to look at how it crosses the x-axis to help us in determining the degree or the multiplicity that it has. And then also determine the y-intercept to help us in finding that value of a. So we have a possible function of what this graph actually is. So we're going to do the reverse process of what we just did. Okay, so I want to end with this, something about important relationships of our x-intercepts and zeros and solutions and things like that. All three of these first things that I have listed here mean the same exact thing. It's just a different way of stating them. So x-intercepts of a graph mean the same thing as zeros of a function, and it also means the same thing as solutions of an equation of f of x equals 0. Now, something that is closely related to zeros are factors of f of x. So if we factor our function, say we have f of x equals x minus 1 times x plus 2 squared. So that is our function, but in factored form. These are factors, but our zeros are x-intercepts or solutions to the equation. If we set this function equal to 0 and solve, we would have our x-intercepts at positive 1 and negative 2. So that there is how all of these relationships coincide with each other and why they are important to know. And that's how I'm going to end it, guys. So I will see you in class. I hope everybody understood most of what I was discussing today. And if you have any questions, please let me know in class, and I'll see y'all later. Okay, last example I have for you. It says approximate the real zeros of our function f of x equals this polynomial. Okay,